what we're going to do now is we're going to go over some different ways in which we can measure changes to gases now. What happens when I try to take a gas sample and do something to it? And we're going to start with Boyle's law. Note that at least for myself, depending on who you're watching this video for, that can change. I'm not worried so much about the name of it, but I am worried about the concept of it. So if names help you remember it, that's good. But I'm mostly focused on just what the relationship is. So there's the word version here, right? There's the inverse relationship between pressure and volume when temperature and moles are constant, meaning if one is increased, the other decreases. So what the picture to the left is showing is that if one way to measure mass, right, is this is set up like a piston, like you might think of something like in a car. If you were to place a mass on top of that piston, what happens is you're increasing the force going down. Since those have weight, they're going to push down on it. If nothing else changes inside the piston in terms of temperature or the number of molecules of gas, so like gas can't get in or out, the piston will have to change its volume in relationship to that. So as you put more mass on top of it, it pushes down. Then the molecules, if it's going to stay the same, the volume is going to have to decrease because you increase that pressure. And so to make it balance out, what's happening is the molecules are trying to collide with the surface. And so if you shrink the volume down, they can collide with the surface more often. And by colliding more often, you're increasing the force inside the container. And you have to increase the pressure, because it's force over an area, it's over a smaller area now. So you're increasing that pressure, and it has to increase enough to balance versus the mass you put on top, which increase the force downwards on it. So you have to balance that out. And so that's a way of measuring this relationship. And you can see the graph of volume versus pressure. That is, pressure is going down, volume will go up, because early on here, right? So over here, this dot on the left I just made is low P because it's at the beginning, but very high volume. And then as it extends across, this is increasing pressure as you go to the right, the volume goes down. That's why you see that pattern. In terms of mathematical relationship, okay, I'm going to click over here so it stops doing the animation. So in terms of the pattern, you get the relationship that P1V1 equals P2V2. And so you could use this to do calculations, but you should also be able to do questions where I just ask, hey, if you increase the pressure of something with the temperature and moles are constant, you should know the volume goes down. So you should look at this as both a concept you can apply as well as a numeric relationship and apply the appropriate one depending on circumstance. So let's look at some problems now with this. So first, a math problem with it. A balloon has an initial volume of 350 milliliters at a pressure of 1.05 atmospheres. If it is compressed at 250 milliliters, what would be the new pressure of the air in the balloon, assuming the balloon doesn't pop from the compression? We make a lot of assumptions in these problems. So if your balloon pops now, you don't have a container anymore, so it isn't a good measurement anymore. But this is going to be my initial volume. This is going to be my initial pressure. This is going to be my final volume. And I want to know what would be the new pressure. That's a good way to know. I want to know P2. And I will also note, before I solve this problem, we're doing this with a balloon because balloons are really nice. You'll see these in a bunch of examples. Balloons are nice because they're elastic. What I mean by that is they're going to change what they're doing. So they can change real easily, right? So that makes it so I can like squeeze it or do it. Like if I've got gas in a flask, I can't easily change some of the volume of the flask because the flask would literally shatter if I tried to change the volume, right? Because if you had a flask in your lab, you seal it up. This is why if you do something that increases the pressure too much, it breaks because the volume can't change. That's why sealed containers are dangerous if you heat them up or something like that because they can't change volume. And so that's why things can do things like explode if you're not careful around pressurized gases and stuff like that. So increased temperature too much, tries to get pressure to go up too much, more than the container can hold, and the volume wants to change. So balloons are nice because those volumes can change. And too much right now, the pressure changes too much, eventually the balloon pops or something, or you try to increase the volume way too much, the elastic stretches so much that it pops. But overall, in small changes, it can do it okay. Now, how do I solve this as a problem? Well, we have P1V1 equals P2V2. And I know I want to solve for P2. So divide both sides by V2. P1V1 over V2 equals P2. Now, something I'll point out with this particular problem is it's okay to leave your volume in milliliters here. For the units that aren't temperature, when you're doing something like this where they can cancel each other out, they're okay to leave in those units. You can't do that with Celsius. And the shorthand, if you'd like to talk to me during office hours, I'm happy to talk more about the math reason related to that. But the short version is that the relationship between Celsius and Kelvin is a linear one. It's not like a change of like a multiplicative factor. And so the change between them doesn't work out like this. You can't work with Celsius when you're needing to work with Kelvin. So that causes a problem. In the case of milliliters to liters, though, when I'm dividing them by each other, the difference is just a factor of 1,000. So that factor of 1,000 impacts both V1 and V2. And effectively, you're dividing both numbers by 1,000, and those divided by 1,000 cancel out. But if you're trying to add 273.15, you can't just cancel out 2 plus 273.15s that are on top and on bottom of each other. Once you do that, it doesn't cancel anymore. So for that reason, in these problems, you can keep things in the units they're in if you're consistent. Now, that's with these things with their changes. Later, you're going to have a constant added in, and with that constant, that will stop being true because the constant will be in particular units. And then you have to cancel with the same units as the constant you're working with. So for this problem, and if you're ever unsure, just convert to the units you know work consistently, because if you convert both these to liters, you'll also get the right answer. But I want to explain why you can leave it in milliliters if you wish. So for this one, we have 1.50 atmospheres. V1 is 350 milliliters. And then V2 is 250 milliliters. Note, it is helpful to write the units here and make sure you're paying attention to which is V1 versus V2. The most common errors are just to flip these things. So it helps to actually label it on your problem. The volumes here will cancel. And so we have 1.05 times 350 divided by 250. So we get 0.14. Oh, wait. I put a number in wrong somewhere, didn't I? I accidentally put 0.105. That would be a much different pressure. There we go. We get 1.47 atmospheres. What I actually just did there is I was making a check in my head. I knew, hey, pressure should go up because the volume went down. And I was about to put 0.147 down, and that is definitely not true. And my brain knew that right away because I was thinking of that relationship. And that's what's one of the things nice with these problems, is a lot of errors will cause you to get answers in the wrong direction. And so if you keep that in mind, hey, what change should be happening? Should it be going up or down? Your most common errors are ones you can catch yourself if you get used to these problems. Like, oh, I know this pressure should go up, but I was going to write a smaller number. What did I do wrong? And then I could catch it real quick. Oh, I put 0.105, not 1.05 in my calculator. Oops. So that can help out a lot. And so that's something I do strongly encourage. As you practice these, that can get helpful if you're paying attention to, is this going the way I expect it to, rather than just plugging my numbers in and not paying attention. Now, let's look at one more. And this one, I'm just going to talk about what would happen. So we're going to talk about a diver. So a diver goes 20 meters under the ocean and holds their breath, and they quickly rise to the surface. And so we've got our little diver here. Stick figure is about as good as you're going to get from me. They're under the water, and they're 20 meters. And so one thing about diving is that the pressure you feel on top of you is much, much greater as you go down compared to the atmosphere, right? Water is heavier than air. I think most of us are pretty confident with that. So you feel your pressure goes up much faster as you go up below the water compared to as you change distance above Earth. Now, on Earth, you can feel it if you go far enough, right? Like you get in an airplane, eventually your ears pop because you have a different internal pressure inside on the other side of the eardrum compared to the pressure inside the plane, and so you can feel that difference. And even though planes' cabins are pressurized, so it's not going to be the same as it is right outside, it's going to still decrease, and you can feel that difference. But water, it goes down very quickly. And so this is the reason a diver can't just go up very quickly without causing some serious problems, because this problem would be the example of why. So 20 meters below, they're going to feel a pressure of about 3 atmospheres. And let's say they float all the way to the top really quickly, and they're not trying to do anything to help it as they go, to change the pressure, and now they're up at the top, and now they're at 1 atmosphere. So if we think about our equation, P1V1 equals P2V2, what should happen to the air inside their lungs? Well, if you went from 3 atmospheres to 1 atmosphere, then the volume has to change in the inverse direction. So the pressure decreased by a factor of 3. It got divided by 3. So the volume should increase by a factor of 3. It should triple. My lungs, if the air inside them, because I held my breath, was suddenly trying to be triple the volume, my lungs would not like that. Now, obviously, this person can't instantly go from 3 atmospheres to 1 atmosphere. Your body is going to try to adjust to that. But especially if they held their breath and they were trying to go really quickly, something scared them or something, and they weren't well trained, it would be very bad. It would cause them to get sick because their body would not deal well with this. It would be like, no, we can't make this change this fast. That's why divers normally have to go up more slowly, because what happens is your body's going to adjust as you go up to, okay, changing conditions of pressure. I need to change how many molecules are in here. I can expel. I don't have to breathe in as many. It can change that part. I can make adjustments. And so that's important, because that's going to, your lungs can't triple in size and your body would be reasonable. So this is an example of how you can think about Boyle's law and how it would apply to different situations, is the idea of how pressure and volume are related to each other. Now, pressure and volume aren't our only property we can measure. We can also look at volume versus temperature. So, 1 second. So we also look at volume versus temperature. In this case, volume and temperature are directly proportional rather than inversely proportional. That means one changes, the other goes in the same direction. So when volume goes up, temperature goes up, and when temperature goes up, volume goes up, if pressure and moles are constant. Notice that this relationship, as well as Boyle's law and the one I'm about to show you, are all cases where two of the four properties are held constant. This is because by holding things constant, we can make better measurements of how they relate to each other. If three things could all change at the same time, it would be hard to tell, which one's causing the others to change. So by controlling how we cause certain things to change and others not, we're able to learn about how those properties work out. And then you get the mathematical relationship, and for a direct relationship, you divide them. You get V1 over T1 equals V2 over T2. So our pictorial representation of how this would work would be if you were to increase the temperature. So for example, applying a flame at the bottom of this, it causes the volume to increase because it has the same mass on top. So the pressure needs to stay the same. And so as the temperature goes up, the molecules start colliding with the walls more often and with more force as the molecules are now moving faster. And that's going to increase, that would lead to an increase in pressure. But there shouldn't be an increase in pressure because the outside is still the same pressure. And so when these molecules start hitting further, that's going to apply a force that allows the container to change in size and volume. And it will increase in volume until the pressure remains constant. Because we said, hey, this is a law that applies when pressure remains constant. So we get this relationship that is linear, that is directly proportional, and you see the linear increase, that is temperature goes up, volume goes up by the same amount, and that's a multiplicative factor. So like if temperature doubles, volume doubles. If temperature triples, volume triples. And specifically, it does this with Kelvin temperature. If I move from 5 Kelvin or 5 Celsius to 10 Celsius, I did not double the temperature, but I did double that number 5 to 10. That's why you can't use Celsius here, because that doesn't give the real relationship there, that 5 to 10. Instead, it's going from 278 to 283 Kelvin. That's not nearly doubling. So let's look at an example with this one now. So we have a version like this. You take a gas, you put it in a container on top of a hot plate. It's going to be low pressure. I've got something on top that measures the pressure. As I increase the temperature in the hot plate, that gas, if it's in a closed container, is going to increase in pressure, and I can measure that. And as the hot plate gets hotter, it keeps getting higher pressure. We can also do something like this with like a balloon. That's what our problem's going to be in a minute. I'm going to use as an example. You could take like a balloon, put it in some ice water. It's going to get smaller. You put it in the hot boiling water. It's going to expand. So you can see the same thing. This leads to a mathematical relationship. This is figure 811 in your text. And so you can see as your temperature goes up, you increase your pressure. In this case, they reported it in kilopascals. We will rarely use the unit kilopascals in this class. I mentioned that it is a unit of pressure, and I'm going to purposely in examples try to use, there are a bunch of different units for pressure. We're also going to get to bars at some point. And if you need to use them for something, I will give you appropriate conversion factors, but I want to mention they exist. Now, let's do a problem with this. Let's say we've got a balloon with a volume of 250 milliliters. I got a balloon in front of me. I don't really, but let's pretend. And then I put it in an ice bath. We want to know what's going to happen to the volume as it goes in that ice bath. And conceptually, you should be able to say, once you've learned this relationship and know it, oh, it's going to shrink because the temperature inside that balloon is going to go down, and that's going to cause the molecules to apply less force. And so the outside pressure is effectively going to collapse on it until it shrunk the area those molecules run into, so now it's applying the same force as atmospheric pressure. And so since pressure is constant, we're going to see a change in volume. So we can keep using milliliters because that unit works okay. It's only Celsius that we have to make the change to. So this is going to be my V1. This, once I add the right amount, I'll have that T1 is 298.15 Kelvin. So I added 273.15. I then have a new temperature T2 of 273.15 Kelvin. And then what will be the new volume? The question is asking what V2 is. So our relationship is V1 T1 equals V2 T2. Now I need to get V2 by itself, so I'm going to multiply both sides by T2. When I do that, these cancel on the right, and I get that T2 times V1 over T1 equals V2. So I plug my values in. My T2 is 273.15 Kelvin. My V1 is 250 milliliters. My T1 is 298.15 Kelvin. And our kelvins cancel. And so I multiply all these out, 273.15 times 250 divided by 298.15. And from this, I will get that its new volume will be, okay, 3 sig figs, so 229 milliliters. So balloon shrunk a little bit, went in the right direction. So you can see this works just like the equation's a little bit different, but it's the same idea as P1 V1 equals P2 V2. The one difference here is when you do the rearrangement, especially make sure you pay attention to what's 1 and 2. Because, for example, here it is T2 times V1 when you end up arranging it like this. So it's good to go ahead and label it in the problem because it's very easy to accidentally reverse these somewhere. So just make sure you pay attention when you're putting numbers in and you'll be fine with these. A third relationship, I can't really do a picture as easily for this one, is Avogadro's law. And it is that volume is also directly proportional to the number of gas molecules in a sample if pressure and temperature are held constant. Critically, this is true for all ideal gases. It doesn't matter what type of gas molecule you have as long as it's an ideal gas. At the end of the class, we'll talk a little bit about what non-ideal gases are, but we're going to stick to ideal gases mostly. And so this leads to the relationship that looks just like V1 over T1 equals V2 over T2. It's just V1 over N1 equals V2 over N2. And so this is just saying, hey, if I have more molecules and the other things stay constant, I have to have more space for those molecules to get those same properties. If I have fewer molecules, I need less space to get those same temperature and pressure properties. And so in terms of, oh, right, that's not there. So we can do that. Problems with this will solve exactly like the one we just did with V1 over T1 equals V2 over T2. They'll be exactly the same. Plug the numbers in. You just don't have to deal with the fact that temperature requires that unit conversion. You might have grams instead, though. So you got grams to moles instead. It's the only difference there. One thing that's nice about all these rules is the three I introduced them in chronological order. Compared to most of chemistry, they're actually a lot more distance here. Like if I remember right, Boyle's law is in the late 1600s. Charles's law is sometime in the early 1700s. Avogadro's law isn't until the 1800s. There's a lot of time between these. And it has to do with different discoveries. So for example, Avogadro's law, in chemistry class, you're learning a chemistry where we're teaching you sort of an order of what we think makes the most sense to teach now. The concept of a mole is, compared to some of this other stuff, much newer. So we don't have the mole until you're around the 1800s. There's a lot of debate about, okay, how do you actually count how many molecules you have? This is not something that is clear before that. The concept of a mole and how that works is not something we've had as long as we've had like the pressure laws here, for example. So these sort of get developed over time. And once you have all three of these laws, we now know all four properties that are going to impact our gases. We can learn how all four of those relate to each other as well. And so you end up with this relationship here, that P1 V1 over N1 T1 equals P2 V2 over N2 T2. And what's nice about this is you can derive any of those relationships from this equation. All you have to do is you cancel out anything that is constant. So for example, if N and T were constant, you cancel them out in both equations. And oh hey, if I cancel those out, because they're the exact same number, right? Like if N1 and N2 are the same, I multiply both sides by the same number, it cancels it out there because of how the equation is written. I get P1 V1 equals P2 V2. You can do this with any two properties and you'll get the laws you just saw plus some others. So rather than trying to memorize them all individually, if you memorize this particular law, you know all of them. And that works out for that. Now on top of this ability to convert between them, we can also do measurements where we don't have to make a change and we're just measuring properties. And this gives us something called the ideal gas law, which is related to all those different experiments that we just looked at. When you combine all those results together, you end up with this law. PV equals nRT. And of all the things in this chapter, you will use this by far the most. We call this the ideal gas law. And this is the relationship between the four properties, pressure, volume, moles, and temperature. And what it means, if you know any three, you can always solve for the fourth. Note that R here is something called the ideal gas constant. This is something that has been measured. This is the relationship between these four properties. And so we plug it in as a constant. Then plug in the 3 units we know, and we can use it to solve for a fourth. I'll also note that the ideal gas law can come in different units. You can know an ideal gas law that uses millimeters of mercury instead. We will stick to this one for this course, but if you see one in another course or in another application, that's okay. So there are different ones that use some different units. And so if you're always measuring something in millimeters of mercury, you might as well use the gas law constant with millimeters of mercury rather than constantly convert back to atmospheres. We're going to use this one for consistency's sake in this class, though. So just to mention, there are other R's that use other units. There's actually in another chapter, we'll look at R in a different context where we do use it with some different units. So R will come back up in the future. Pay attention to the units of R. We'll choose what units we use based on the problem we're solving. So let's look at an example of how we would do this. We're going to calculate the volume of a 0.520 mole nitrogen gas sample if it has a pressure of 1.76 atmospheres and a temperature of 310 Kelvin. So our rule is PV equals nRT. And what I know, I've got an N here, I have a T here, I have a P here, and I want to calculate the volume. That's question mark. So I'm going to rearrange this equation to solve for V by dividing by P on both sides. V equals nRT over P. Now, one reason I'm using this law, instead of the P1, V1, any of those things, where it's like P1, V1 equals P2, V2, here I have a gas that nothing has changed about it. It's just asking me, hey, if the gas happens to have these properties, what will this other property be? If there was a change, it's often good to go to those other equations. But for this one, when it's all at just one condition, we're not expanding the gas, putting more moles in, we don't have a temperature increase or something, this equation works well. So if I plug these in, this time they're already in the right units. We'll look at an example after this where they're not. But we've got 0.520 moles. R is 0.08206 liters times atmospheres per mole Kelvin. Our temperature is 310 Kelvin. When we divide that by our pressure is 1.76 atmospheres. So if we check our units, our atmospheres, our moles, and our Kelvin will cancel. And then I just have to plug a bunch of numbers in. And so from that, I get that the volume would be 7.52 liters. So that would be the volume of my gas if I had those exact properties. So we know any three, we can find a fourth. Let's look at one more example to show that. Now, for this one, I suggest you pause this, try to solve it yourself first, and then watch me do it and see if you get the right answer. Okay, hopefully you tried to solve it. So let's start by getting things in the right units. So I've got a volume, temperature, and a mass, but none of them are in the right units yet. So I'm going to start with the hydrogen. So I have 2.8 grams of hydrogen gas. As a reminder, hydrogen is one of our diatomics, so it's going to be H2, not just H. So it has a molar mass of 2.02 grams per 1 mole. So that's going to give me, I'm going to keep an extra sig fig. In my final answer, I only have 2 significant figures here. That's going to limit me. I'm going to keep an extra one, though, when I'm doing calculations so I don't run into a rounding error. But this is going to be 1.39 moles of H2. Now I've got the volume. My volume, at this point I'm okay if you can just say, oh, that's divided by 1,000, 0.7500 liters. So I divided it by 1,000 to get from milliliters to liters. And then our temperature is going to be 28.5 plus 273.15. When I do that, I'm going to get 301.65 Kelvin. And so now I have this in moles, liters, and Kelvin. Those are the units I wanted, and now I have to solve for P. So again, we have PV equals nRT. Sorry, I should have muted myself there. So pressure equals nRT over V. So pressure is going to be 1.39 moles times 0.8206 liters atmospheres per mole Kelvin. We have a temperature of 301.65 Kelvin. Dr. Leslie didn't quite leave himself enough room, but it's close. It'll be okay. And then volume is 0.7500 liters. Now we check, moles will cancel, our liters will cancel, and our Kelvin will cancel, and we'll be left with the atmospheres like we would expect. It's a pressure, so we should get a pressure unit. Multiply all these out. And this is a very high pressure system. Dr. Leslie set this up actually just earlier today without calculus. But hey, you can have a high pressure gas. So this would have to be in something like a cylinder or something to keep it so that it was very strong. So 45.9 atmospheres, which actually, based on my sig figs, would only be 46 atmospheres. I only have 2 sig figs. So yeah, reasonably high pressure gas. Would want to be careful with this thing. So also hydrogen is explosive. So definitely be careful with this one. So that's how you solve this. And this goes through all of the different unit conversions. The problem just said calculate the pressure. Do pay attention if units matter. If the problem asked you to calculate the pressure in millimeters of mercury, you should multiply this by 760 to convert between atmospheres and millimeters of mercury. So just pay attention to your units. They come up a lot in these problems because there's a lot of units, different UAs. We can make these different measurements, and they have to be consistent with the constant that we're using. And especially when it comes to temperature, because even when we don't have to use that gas constant, we have to make sure we're working in Kelvin, not Celsius. And it won't really come up much in this class, but not Fahrenheit either, right? So Fahrenheit would have to go to Celsius than Kelvin, or you'd have to look up what a conversion direct from Fahrenheit to Kelvin is. I'm sure there is one. I know there is one. I just don't know what it is off the top of my head because I just don't do that very often. So you will use this ideal gas law a lot. In one of my future videos, we'll look at the idea of how we can use this to then do calculations of moles. And, oh, hey, look, if you can get to moles, this is a preview, we can go to moles of other things. We can use this now to do a balanced chemical equation. So just like the few previous chapters, this is another chapter which is, guess what? We can find a way to solve moles so we can use balanced chemical equations. So ultimately, this is why it's particularly important to chemists. We're really interested in calculating moles. That helps us a lot. So you will use this equation a lot, and later on in the chapter, you'll be using it where this is a start of a problem. Find the moles first, then do a limiting reactant. Do a theoretical yield, do a percent yield. All those things we did in previous chapters will come back up, but now with gases. So we got a couple of other things to define real quickly with gases, and then we'll be done for this video. So first, we sometimes have to define something called standard conditions. So standard conditions, we call standard temperature and pressure, is 0 degrees Celsius, 1 atmosphere. There's a note here that I figure it's good to include from your text. I use 1 atmosphere so often that I forget this. Technically, 1 bar is recommended for standard temperature and pressure, but texts generally use 1 atmosphere, so I'm going to do that to be consistent with how most textbooks do this. And so, what this means is that at standard temperature and pressure, the volume of 1 mole of gas can be calculated. It's exact because the temperature and pressure are constant, and so if you have a mole, that's 3 of the 4, you can actually figure out under standard conditions what this is. This is also helpful for things like constants, about other properties about a gas. You would look them up. We have to have an agreed upon set of temperature and pressure. I don't want to have to go to, okay, where's the guide for if I have a gas at 38 degrees Celsius and a pressure of 0.92 atmospheres? Well, that would suck to look up. So instead, we agree this is what things are going to be written in, standard temperature and pressure. You can then take your answer and then apply your relationship P1V1 N1T1 equals P2V2 into T2. For the ones that aren't standard, you can plug this in and you can solve for the thing you need to know. So it lets you, like standard will be your 1 values, right? And then you can plug in values you know over here on 2 and make the change over from standard temperature and pressure to your specific situation. So like if you know your pressure and volume, you can plug those in. You can plug in standard values, and then you can solve for N, for example, and then you plug in the temperatures. Like you plug in 273 on the left side, and then whatever your actual temperature is on the right, and that lets you make the adjustment to solve for N, for example. So what's neat about this is it turns out, and this is a kind of cool conversion we use occasionally, is that no matter what gas you have, a single mole of it always occupies a volume of 22.4 liters at standard temperature and pressure. So the 3 used from the figure from your text was helium, ammonia, and oxygen. Those masses are all the masses of 1 mole of that gas. Even though they're very different molecules, 1 mole will have the same volume. And this is the idea within our ideal gas law, and we'll talk eventually about what can make something non-ideal. But a lot of gases behave as ideal, especially at interactions we tend to encounter in everyday life. Most gases are ideal, which is really, really good for chemists. Most chemistry was actually discovered through gases. And they didn't know about non-ideal gases at the time, so we're really, really glad the ideal gas law is good, or chemistry would have been way even harder to learn when we learned properties, because a lot of the stuff about what a mole is and things like that all got learned by chemists studying gases that they captured, because they could measure them really well, and they could figure out, oh, these relationships, things like 1 to 2 mole relationships, like we take for granted now. Balanced chemical equations exist. Up until, I don't know the exact date we've really got balanced chemical equations, but like even in like the 1700s, you have some issues because the mole doesn't exist, and we have the idea that like fractions of a molecule exist, about, oh, like one volume equivalence, like one volume equivalent of hydrogen versus one volume equivalent of chlorine will make make HCl. But they can get that, but we still don't have the idea of a mole, so that's still coming out even in the 1700s. So thankfully this all works. We have one other property to talk about real quick, and then make sure, I'm going to click through a slide real quick. Yep, this is the last thing I want to do in this video. So we know that density equals mass over volume. We can plug this into PV equals nRT and do some rearrangement, and you get this equation here, which on my next slide I'll show you what that stands for rather than having to worry about it here. Let's just do it here. Same equation, nothing's changed. So because density is an intensive property, it doesn't matter how much there is, so it's not related to the number of moles. So the density of a gas is related to its pressure, temperature, and molar mass. Oh hey, it turns out the density can be related to what we have, because if you know the density, you can figure out based on what its molar mass would be. So these two things are related to each other. So let's look at how I would solve a problem doing something like this. So we know that density equals molar mass times pressure over RT. So this one is one where it's helpful to see a problem like this, because sometimes you don't think about how certain things actually give you the information. So this problem actually gives us enough to solve this, although it might not be obvious initially. The reason for this is they tell us this is oxygen gas. Oxygen gas is O2. Oxygen gas has a molar mass of 32 grams per mole. Hey, they gave us a molar mass, they just didn't put a number in the problem. We have a temperature of 55 degrees Celsius. Now that's familiar. We've just got to convert that into Kelvin. So you get 273, that's 328, right? I'm going to make sure. Good. I didn't want to write the wrong answer in the video and confuse people. 328.15 Kelvin. We then have to get our pressure into atmospheres. So we have 725 millimeters of mercury. So it's a little bit below an atmosphere. So we have 760 millimeters of mercury is 1 atm. Those cancel. And so we have 725 divided by 760. And so that is 0.954 atmospheres. So we can find out what would be the density of this oxygen gas at these particular set of conditions. So density equals molar mass, 32 grams per mole, times our pressure, which is 0.954 atmospheres. We then have our gas law constant, 0.08206 liters times atmospheres per mole Kelvin. And then we have our temperature, which is 328.15 Kelvin. Now if we check, the Kelvin units cancel, the atmosphere units cancel, the moles cancel, and we're left with grams in the numerator and liters in the denominator. Oh hey, that's a density unit. So density is going to be equal to 32 times 0.954 divided by 0.08206 divided by 328.15. And so this will be 1.13 grams per liter. Note, you would need to check the problem. This problem didn't specify what density units you had to use, so this is okay. And we most often use grams per liter for gases, but if you wanted, it might ask for it in grams per milliliter. You would then need to convert it from grams to liter to grams per milliliter by multiplying by 1,000. Check that your units work out when you do that. Yep, 1 liter, 1,000 mil. Yep, that would work. I'm going to do the conversion real quick in case I said that backwards. I did say that backwards. This is why we check things. So 1 liter is 1,000 milliliters. Yeah, divide by 1,000. Sorry for misspeaking, but there you go. So that would cancel. You would have that 1.13 divided by 1,000. So you have 1.13 times 10 to the negative 3 grams per milliliter. However, gases are not very dense. That's why we tend to report them in grams per liter, whereas things like liquids and solids are way more dense. That's why we tend to report them in grams per milliliter. Both units can be used for the other substance, but it's less common to do so. So I mentioned that because I know we did so many density problems early in the semester, but we always use grams per milliliter because we're working with liquids and solids rather than gases where there are way fewer molecules. So grams per liter tends to be a pretty good unit here. Note, again, you have to pay attention to units. There are a lot of units in these problems. And this one, there were 2 units left, and that made sense because density is an intensive property. It is mass per volume, not just one thing like mass or volume. So this means that you could be able to solve for something like a density. On the other hand, if you were given the density, you could also solve for a molar mass. You could do this in the reverse, solve for molar mass. Note that if I rearrange this equation here, so I'm just going to do this to the side to show you what you would do, you would have density times the gas constant times temperature over pressure equals molar mass. And that's just from algebraic manipulation. I multiplied both sides by RT to get it out of the denominator, and I divided both sides by P. If I solved for the molar mass, I could then figure out what gas I had. So for example, if I found out a molar mass of 2 grams per mole, well, that's pretty close to hydrogen. So I wouldn't just ask you out of the blue, pick a gas randomly, but I could ask, hey, this sample could be one of 4 things. Which do you think it is? Based on, and I give you this information. Here's a density, here's a temperature, here's a pressure. You calculate the molar mass, look at the different gas options, one of them is going to match up versus the other. So that's a good place to stop here. So far we've been, and I'll mention just for our next video, what we're going to move into now. We have 2 big topics. One is dealing with samples where you have more than one gas present. Things like, oh, when I breathe in the air, there's not just one type of molecule. That changes some things that we have to deal with. And 2, how do I do this with chemical reactions now? Like, we've learned how to calculate this stuff, but this is all of one thing. Nothing's changing chemically. And we're chemists. We want to make new molecules or break molecules or do stuff with them or watch them explode or something, right? So if I want to explode some stuff that's a gas and I need to have so many molecules, how do I do that? How do I make calculations related to that? So that's what we'll be doing later. And this will finish up the calculations of individual properties of a gas molecule here.